Alright, so now we come to another operation on vectors, and so let's see. So there is another operation on vectors which we call as the vector cross product. Okay, and we're going to define the vector cross product, and after that try to tell you why we define it like this, and second is how to calculate the cross products efficiently, because this is again, like the previous examples, will prove helpful to you in your calculations in physics. So this time two vectors will be taken and an operation be defined on those vectors called A cross B, and the answer is going to be a vector. Unlike the previous time in the dot product, the answer was a scalar. Just to remind you again, so A dot B, the answer was a scalar, and but let's not forget this, here the answer was a vector. So in the process of giving too much importance to these two operations, we should not be stupid enough to forget the first operation, which is extremely crucial, and it's a vector. And we do know the properties of this, we do know the properties of this, and yes, now the question is, what is the operation and what are the properties? So let's first ask the question, what is the operation? What is the operation? A priori, I would like to tell you that why are we going to give so much importance to this. So let me again tell you what are the laws of physics that we are exposed to at this minute. This is the key law, rate of change of momentum of the system, which you understand. The meaning of these symbols happens to be equal to the force external at every instant of time. Perhaps let's also, it looks messy, but it's worth writing all of this. So at every instant of time, the force external on the system will be equal to this, and the key part is that there are vectors on both sides, and we've managed to exploit this law so far with vector addition, and actually also vector dot product when we use the conservation of energy. Okay, so the conservation of energy, so this is one law. Okay, I'm sorry, I have jumped the gun here. The second law that we are used to can be stated, so for a system of particles, I said let's call this as the work energy theorem. So the work done, F dot ds, will be equal to the change in kinetic energy. So for a system, this particular conservation of energy in, I'm sorry, this is getting a little confusing. The conservation of energy for a system, I said let's just take it as a law, and in exploiting this law and stating it carefully, we've used the dot product. Now the dot product is here. Okay, there are vectors here, force, displacement. Alright, and because it's a dot product, we get a scalar on the left hand side, and of course we have a scalar, that is the energy, on the right hand side. Okay, and here there are vectors on both sides, but we're comfortable with it because of our mastery over the operation of vector addition. So these are two big things, big two laws of physics, and there's a third one coming up which can be stated very clearly and very simply and very symmetrically. So I'm just writing this again because I really want you to keep writing this and keep seeing this as many times, okay, just to tell you how important this is. Okay, the next law, which is going to be the almost the um, final coffin on mechanics, final nail in the coffin of mechanics, it's going to be like this: tau, okay, external on the system, will turn out to be a vector, will be equal to, mind you, again and again, this is a law. So in other words, we've discovered it by experiments. Okay, and yeah, people were brilliant enough to see it from the experiments, and yeah, mainly Newton. This is equal to dl by dt, where L is called a vector called angular momentum. Tau is a vector called torque. And now this one is looking so similar to the previous one that there is a comfort zone. Nevertheless, it's not as easy as the previous one. So what I mean is that this is a couple of things you should immediately note, that this is another law, and it has come through experiments. But very important for you to realize that these two laws, okay, angular momentum of the system, these two laws are independent laws. Okay, meaning that this is not a consequence of this. So law 1 is not a consequence of law 2, and neither is law 2 a consequence of law 1. These are two independent laws of nature, and they were discovered by experimentalists with their experiments, and together they do give us a lot of predictive powers. What we are focusing on right now is the fact that this very important law can be expressed so compactly because of our background of vectors. Now, I'll tell you that there is a standard confusion, okay, and you should read about it in Klepner and Korenkow, or for that matter R and H. And now any good book will take its time to emphasize this fact, and therefore you should read both the good books and what the author has to say about the fundamental laws of physics, something as fundamental as this. So this particular law, and they do like I said, look symmetrically nice. They do give the same information, and when the system is a single particle. Okay, so they're making the statement that they do collapse into each other if you're talking about a single particle. So one thing is for sure, when talking about a single particle, there is no requirement for two different laws. And therein lies the confusion for the beginning student, who often sometimes is misled by not so great books into thinking that this is a consequence of this, or that is a consequence of this. Okay, and now that you will read K and K and R and H to convince yourself that they're two separate things when we come to a system, and mostly we are interested in a system of particles. A particle, single particle, would be too restrictive. But having said that, there is another nice caveat to the whole thing, that sometimes, I mean, this is surprising, but I think there are considerable number of examples to prove this. Um, okay, so I just want you to read K and K carefully, because he does take his time to prove one small point here, that indeed there is little doubt that these two laws are the same if it's a single particle. So it's actually, he takes his time first to convince you about this fact that 1 and 2 are the same thing for a single particle. Having said that, the caveat is this: sometimes this is more powerful as a problem solver, even if that is, we're talking about particles. Okay, so and then he tries to justify this with some brilliant and at least nice and important examples. I mean, they are not just problems for fun, but they are indeed of some consequence. So do go through this in the book and convince yourself that uh, this law in this form can be a very efficient problem solver, even if it doesn't give you something different from this in the case of a single particle. Okay, so now we're coming back to vector operations. So we have an important law now to analyze, and the first thing to analyze is that what exactly do you mean by what is torque, and what exactly do you mean by what do you angular momentum. Now, for both these things, you need to this can be answered with the help of cross product. Okay, so that's why we are now very much interested in the so-called vector cross product, immediate concern. There are other times when you'll come across the cross products in physics, but let's just focus on torque and angular momentum. Now, um, so why is it that torque and L are so, I would say, a little bit non-intuitive when we define it? We cannot give a simple definition without using cross products. Well, we don't know. This is not the kind of question that I can answer immediately. But having said that, the law was discovered and found to be powerful by experimentalists, and it is a fact of nature, and that can be expressed very compactly. So therefore, we just accept it as a law and try to understand what the law is saying, because the law has been verified in the form that is given and with the definitions that are given um, over the years. So what is the definition of torque? Okay, so torque is equal to a vector, the position vector, cross F, where F is the force vector and this is the position vector, and the answer is a vector. Okay, next, angular momentum is a vector which is equal to r cross the linear momentum. Okay, so these two, okay, let me say it's for a particle. Okay, for a particle, right? So r is the position vector of the particle, F is the force on the particle, and F external if you want, and then this is the torque due to this force, and this is the momentum of the particle, and this is the position vector of the particle. And implicit now, as you can see in both the statements, are the fact that we do have a coordinate system. which is obviously inertial, and that helps me to unambiguously tell you what is R. So definitely there is a coordinate system, there is an origin from where the position vector has been drawn, and you are able to tell me the components of the force. You're able to tell me the momentum of this particle in this coordinate system, and then you can calculate tau in this coordinate system and L in this coordinate system. Also implicit in the statement of the law is that you're calculating torque with respect to inertial coordinate system. You're calculating L with respect to an inertial coordinate system, and the fact that you're using the same coordinate system for doing the LHS computation and the same coordinate system for the RHS computation. So once again I repeat, you need the position vector, you need the force in that coordinate system, and you need the position vector and the momentum of the particle in that coordinate system, and then you can calculate L in that coordinate system and tau in that coordinate system. And when you are applying the law, you have to do both with the same coordinate system, and it has to be inertial. Okay, having said all this, what is the cross product? Now I've been very careful not to write it as F cross R or P cross R. So for example, if I interchange this, it's wrong, and we'll see in a minute why it's wrong. And if I interchange this, it's wrong. Okay, so so now let's get back to pure vectors. I've tried to tell you why it's of crucial importance. It's of crucial importance if you're going to step into the next law. So here's the definition of a cross product. So you take some vector A, okay, take another vector B, and the question that is being asked is, what is A cross B? The answer is that this is a vector, and therefore it's called vector product. We're going to call it the vector product, vector cross product. Okay, and how do I get C? Right, so now it's a vector, so I need to first tell you two things. One, I need to tell you its magnitude, and the other thing, I need to tell you the direction. Okay, now the magnitude is going to be mod of A into mod of B into sine theta, where theta is the angle as you go from A to B in the anticlockwise direction. Right. Next, you need to ask what is the direction. Now the direction is something known as the right hand rule, something that you're familiar with. So you keep your right hand with the fingers in this direction, so your four fingers are aligned in this direction. Then one second, yeah, four fingers of the right hand are aligned in this direction. Then you curl your fingers in the anti-clockwise direction towards B, and then stick your thumb out. So in this case, the thumb is coming out of the plane of the blackboard. It's perpendicular to the blackboard at this point, and this is represented out of the plane of the blackboard is represented like this. So now if you were to do B cross A, for instance, so suppose you were to do B cross A, okay, suppose I were to do B cross A, then the magnitude would be mod B mod A into mod A into sine of what is this now, 2 pi minus theta, and I'm already in trouble. Give me a second, I am struggling a bit here. Okay. Okay. All right. Right. So pi sine of 2 pi minus theta is the same thing as is equal to this as minus of mod A mod B sine theta. So right, so how do you interpret this? One way to say is that I'm going to curl my fingers from B to A, and in which case I'll find that the direction is into the plane of the paper, which I'm going to call it like this. So the magnitude in terms of length is the same, that is mod A mod B into let's say mod of sine theta, and the direction is always going to be given by the right hand rule. So for example, if I do B cross A, what I've realized is the magnitude is same, but the direction is opposite of A cross B. Okay, so in this case A cross B is out of the plane of the paper, and B cross A, which is of the same magnitude, is into the plane of the paper, which I'm going to show like this. The end result of all of this is that the magnitude is same but the direction is different, and the way to represent this is put a minus sign here, and therefore we come across the most important property of vector cross product, which is that it is not commutative, but neither is it extraordinarily complicated. It is just minus of A cross B. Now this is very crucial for us. A cross B is equal to minus B cross A. But there is one distributive property, which is A cross B plus C, which happens to be A cross B plus A cross C, and there is a similar graphical proof for this. Which I shall simply post it to you. It's not so crucial to know the details of this proof. The diagram is a little more complicated than the previous one, but I think it's important for you to realize that these two properties you can use to simplify your calculations with cross product. Now once you learn the standard tricks of the calculations of manipulating cross products, your life will become easy to evaluate torque and angular momentum vector, and also to use the law. Okay, so I'll focus on the calculations in the next video, but I shall end by saying that you know how to define the cross product. That's the one thing that we have achieved. We know that it's not commutative, but the this particular property is pretty easy to remember, and it's also interesting that the distributive property is valid, and we'll use all of this. Alright, I'm going to stop now.